instead of seeing that strangeness or the weirdness of these different laws of physics as a nuisance, we're trying to use them to solve computational problems.
Today's episode of the podcast, number 3 in the quantum series, I speak with Tom Wong. Tom is a quantum computing researcher and physicist working at the intersection between physics and computer science. And today, he talks with me about this technology that could revolutionize the way we live life. He explains what quantum computing is, from how it operationally differs from classical computing to how it is actually an entirely different way of computing and should be treated as such. Tom also discusses some of the real-world benefits and concerns about this technology, particularly how quantum computing could drastically advance our pursuit of higher-tech medicines and vaccines, but also the potential vulnerability of our current information if we don't prepare for a quantum computing world now. Lastly, at the end of the podcast, Tom provides some places and recommendations if you want to learn more about this field.
Mind-bending chemistry.
I don't care. He wants to kill me.
I'm as mad as hell, and I'm not going to take this anymore!
Why do you think it has attracted the public? I guess the name is interesting. The idea of it is interesting in a way that maybe other facets of science aren't.
Yeah, I think one thing is exactly what you pointed out, that the name quantum computing is very catchy. Right. I mean, when I started grad school, I actually wasn't sure what field of physics I wanted to go into, but I had heard of quantum computing. I was like, oh, I like quantum mechanics, and it's like, and obviously, like, everyone grows up with computation and computers and our phones. And so I was like, oh, that just sounds like a really interesting field. I have no idea what it really is, but
two things
I want to
together.
check it out, Yeah. And so, I Googled and saw if there's any professors at my university who were doing quantum computing, found someone, and, I ended up liking it and staying with it. And I'm still in that today. But it's right that it's a very good name. It's very catchy, and it was certainly catchy enough to draw my interest, to learn what it really was. Aside from that, I think one of the recent changes in the field is the big support that we've gotten from industry. Historically, quantum computing has been mostly a research area at universities and academia. Playing a very long-term game. But now that the technology has grown, there's a lot of industry players that are involved. If you name almost any tech company, the big ones, IBM, Microsoft, Google, Intel, they're all investing heavily in quantum computing now. And besides these established tech companies, there's many startups as well. And so because there are startups and investors involved, these companies need to justify that they are spending the money well and in a way that will create returns for these investors. And so there's more pressure to make stronger claims about what the current quantum processors are capable of, or make bolder or maybe more optimistic claims about the timeline of things in terms of how quickly quantum computers will be ready for market. And so I think these various economic factors have played in, and it's also once something catches enough attention from the media, it tends to just snowball. So then other media avenues see what's being covered, and like, oh, this is what's catchy right now, and it's what's drawing clicks and eyeballs, and so we should be talking about it as well.
Yeah. Do you think there's something about the word? Generally, the word quantum. I mean, the word quantum really, there's always that joke in the sort of science meme that anytime in a movie you need to explain something that's unexplainable, you just slap the word quantum on there. There's got to be something about that to it too, right?
Absolutely. Actually, like, especially with the Marvel movies that have come out, I would say recently, but actually, now that I think about it,
spans a lot.
It's been quite a while actually since Marvel started their cinematic universe. But it's incredible how much quantum is referenced as a way to justify their plot lines, especially Ant-Man. Like, basically everything's quantum. In fact, I think Ant-Man 3 that's coming out, it's like Ant-Man Quantumania, I think is the name of it. And they're just diving in headfirst into this idea that quantum justifies all of their plot lines. And we know that, of course, with movies, that they are taking a lot of um, artistic liberty, let's say,
Shall we
in their
say,
use of
yes.
that. But one of the benefits is, as you mentioned, that it's made quantum so much more um, commonplace to people, where people are aware of this term, where even if they don't know what quantum physics is. I remember this was pre-pandemic. Um, so every year we have an outreach to high school students, and they
Okay.
come to campus and they do these different physics activities, and they're trying to see which team is going to get the most points and
Right, right.
win. And so they rotate through different stations, and so at the station I was at, typically we'd finish a little bit early. We have, 5 minutes at the end, and I just ask these high school students if they have any questions for us about what college is like. Do they have any questions about physics? And I think that might have been the year that Endgame came out, actually. I'm not exactly sure on the timeline, but several of those groups of high school students asked us, "What is quantum?" Or like, "What is
Right.
the quantum realm?" Because that's the lingo that's used in these
Right.
movies. And then it was this incredible opportunity for us to explain quantum mechanics to them. And so, yeah, we are definitely seeing people get interested in quantum because of these exciting movies. And you also see this misuse with products, where a lot of products that are unrelated to quantum mechanics are sticking quantum in front of them. So I think Duracell batteries, they had like a quantum line for a
Right.
while. I saw some like soap that was also like some quantum. So, basically
Cleaning effect.
yeah. And
Yeah.
so, companies are adding quantum to everything to make it sound more high tech, even if
Right.
it's not related.
I guess we have that with a lot of different sort of words. Even natural is a perfect example of it, right?
Mhm.
There's so many scientific words that certainly get in there, and I guess that sort of begs the question again, extending about the question about relevance is with a lot of things in science, the timeline of relevance really differs greatly. Okay, and
Mhm.
a perfect example of something that's, should we say, short and very direct in terms of relevance is like the coronavirus vaccine, right? It's
Mhm.
happened really quickly. Not only that, getting the vaccine is going to affect you personally. It's going to affect your
Mhm.
health, and it's going to affect the people around you in the way that you live.
Mhm.
On the flip side to that, famously, with the advent of quantum mechanics, that happened 100 odd years ago, and it wasn't even able to be relevant or used for another decades and decades and decades because the technology
Mhm.
basically had to catch up. And although everything we do now technologically has something to do somewhere with quantum mechanics, the effect is much more diffuse. We don't notice it in the same way that we might notice a coronavirus vaccine, like I mentioned before.
Mhm.
So with that in mind, what sort of effect and what sort of timeline are we expecting with quantum computing? Is it something way off in the future that we're barely going to feel, or is it something immediate that we're going to feel huge changes for?
That's a very good question. I think it depends on how one feels the impact of a new tech tech technology. I think in some sense, was it? I mean, even with classical computing,
Right.
there are new breakthroughs and faster processors and all these things that are happening very regularly. But I don't know if the average consumer actually feels that, because
Yes. Good
the
point.
laptop or computer or smartphone that they buy generally aren't using these new uh, breakthroughs in classical computing for a couple of reasons. One is that anytime there's a new technology, those things tend to be very expensive, and so the average consumer, when they buy a laptop, doesn't need those technologies in order to check their email or to write a Word document or things like that. And so, it's going to be companies that are buying these things, or big data centers, or big supercomputers that it will be utilizing these breakthroughs. And so, in some sense, consumers are already not feeling all these, uh, innovations in classical computing, and I think it'll be similar with quantum computing as well, where the average person doesn't need to buy a quantum computer to check their email faster.
Right.
But there may be some very specialized problems that researchers or businesses are trying to solve, where it would be advantageous for them to try to solve those problems on a quantum computer, just like they would buy some time on a giant a super computer as well. And so,
Okay.
these supercomputers exist in our lives, in the sense like, they are driving so much innovation um, and things like that. So in some sense, like we've all felt the impact of supercomputers, but we haven't felt them because we don't own them.
Right.
Although, one could argue that our smartphones are supercomputers compared to the computers that landed people on the moon,
In the past,
but
right.
and yeah, from the past. But there are all these technological devices that exist that we don't really feel. And you know, I mean, a very simple example is like, most people don't buy dedicated graphics cards unless you're a gamer or you're doing, some 3D modeling or things like that. And so like my laptop doesn't have a dedicated uh, graphics card or GPU. But if I do need to solve something that would benefit from the processing power of a GPU, then it's like I can just go to a desktop computer in my lab with a GPU,
Right.
run the code there, or offshore to the cloud or something like that. And so I think certainly in the near term, while quantum computers remain very expensive
Right.
and I think if there's people who have a need for them, then they'll just offshore it or they'll just have it as a separate unit from their laptop.
Right.
So you can imagine that there could be like a instead of a CPU or a GPU, there might be a QPU in the
Right.
future.
The extra step. So you sort of you're saying that a lot of the things that we, I suppose, are feeling now as a result of supercomputers, things, shall we say, I suppose, this is me just guessing right now, things in economics, things in medicine, where we need to huge amounts of numbers fast. It's just going to be similar things to that, but times by a lot more.
Exactly.
Okay.
Yeah. So I unless you have a quantum computer in your pocket, I feel like the average consumer isn't going to feel the impacts, but they actually will be feeling the impacts, through medicine and economics and all these things that you mentioned.
Got it. And is this going to be sort of more of a trickle? We're going to see things slowly ramp up, or is it more of a case, in terms of the research, that we're waiting for that specific breakthrough that's going to make, for lack of a better way to put it, quantum computing here and now? Are we just waiting for something specific?
I think there certainly are milestones that people might liken to these big breakthroughs that we need to happen. But the way that these things happen, and even with the history of science in the past, is that these are all slow, incremental steps that we take, and so there are certain breakthroughs, but the progress of science feels very, step by step. And so that's not always evident to the public because it typically doesn't make headlines until we have that big news. But I mean, even, yesterday with the new Mars rover landing, it's like suddenly the public is very aware that, oh, wow, there's this new rover that's landing and it has landed, thankfully. But they don't see the years and years and years of work that NASA scientists and engineers and scientists and engineers from other organizations were, all this work that they put in to make this happen. And so, for the public, it seems like, wow, there's suddenly this breakthrough. We have this new higher tech rover on the surface of another planet. But to the scientists, it's like, no, there's all these steps we had to take to reach all these milestones, to get all these components put together to have a functioning rover. And so I think quantum computers will be like that as well. There's a lot of great progress that scientists are making day in and day out. And every now and then it comes together as a big press release or a big paper, and we can share like quantum computers. Hopefully, I'm talking about in the future, hopefully we can say quantum computers can now fix and correct all their errors and noise that they experience. Because currently our quantum devices are very noisy. Okay. So that, for example, would be one of those big milestones.
Right. I that's a great analogy, and I've spoken to people who have mentioned these sort of things, that in these really, really big worldwide events, something like quantum computing, or definitely with the recent Mars rover landing, we see that number one event, and we picture it as that, but there's whole departments of people just trying to work on how the tire is going to work on the rover, for example. And it's just not interesting really for the general public. It's not exciting, but it's so utterly crucial. And it's a perfect example. And I'm sure there's sort of similar analogies inside quantum computing too.
Yes, exactly.
Now, I guess that leads us on to the next part. I try my best not to ask, I suppose, the most generic questions that you can Google and find out, but we do need sometimes some more generic questions.
Of course. That's fine.
Number one most important question: what is quantum computing? Why does it differ from everything else that we have now?
Yeah, that's a great question. So our current computer, so I'm assuming that it's the quantum part that needs explanation.
That's right.
The second part with what a computer is, people engage with computers very regularly. So there's a strong sense for that. So our current computers, now, at least in our field, we like to call it classical computers. They compute using the laws of classical physics, kind of ordinary day-to-day physics in our human size scales of, length and mass and things like that. But it turns out that microscopic things, so atoms and particles and molecules, it turns out that they behave very differently from our big macroscopic classical world. And so we had to come up with a new set of laws and formulas to explain how these very different particles act. And that is what we call quantum physics. So it's a set of laws of physics to describe typically things that are very small, and it's just completely different from how our big world acts. And so what we're trying to do is, instead of seeing that strangeness or the weirdness of these different laws of physics as a nuisance, we're trying to use them to solve computational problems differently from the way our current classical computers do. And so it's about doing computation differently, not doing the same computation we're currently doing, just on like a bigger scale. So a quantum computer isn't just like supercomputing in the sense of we're doing classical computing bigger. It's about doing computing differently by changing the laws of physics.
Right.
And so I like to explain it actually using sports. So I'll use soccer, or
Please.
maybe you'll call it football, and many of the listeners might call it football, but I'll call it soccer. So the reason why it's more often called football is because you generally can't use your hands.
That makes
play
sense.
with your feet, right? And so soccer maybe loses that notion a little bit.
Right.
But yeah, for the most part, you have to use your feet and you can't use your hands other than certain circumstances. You're the goalie, or you're throwing the ball in, right? But for the most part, you use your feet. And because of those rules, the game plays out a certain way. Let's say we change the rules. So we're changing the laws, where we change the rules and we say now you are allowed to use your hands. So if players are now allowed to use their hands, there's certain things that they might be able to do faster by just throwing the ball to a teammate. But not everything is necessarily faster. If you want to get the ball across the field as quickly as possible, kicking it is still probably faster than throwing it.
Okay.
And so it's like that with a quantum computer. We're changing the rules or the laws of the game. So now the computers can use their hands, so to speak. And in some cases, they can do things faster than classical computers can, but not in all cases. In some cases, kicking the ball is still fastest.
Okay.
Yeah. So I like this analogy because it communicates the notion that quantum computers are not just faster at everything. They're only faster at some things.
That's interesting because, I've always had it, and I'm sure the majority of people do, where it's like, I've pictured it as a stack on top of, other computing, when it's more filling some gaps that regular classical computing might have, and also maybe extending it also.
Exactly. It's not more classical computing, it's different computing.
Okay. And what is the difference with it? I think hopefully most of the listeners will understand the basics of computing, the very, very lowest level. So what is different about it?
So first of all, this is a very active area of research. Right. So there's certain aspects about quantum physics where we utilize them in different quantum algorithms, but it's actually not known if those are necessary. It's just with our current knowledge of how to develop quantum algorithms, those properties have been useful, but it might be possible that we can simplify things and not use those quantum properties. And so, and in fact, in some sense, we don't actually, well, yeah, maybe I'll just stop that over that.
That's fine.
And so, but I'll give some illustrations of what makes
Okay.
quantum computers different from classical computers. At least, the things that we can easily identify. So we'll just start with a bit.
Hmm.
So with a normal classical bit, it has two states that we typically call 0 and 1, and that's it. So a bit actually stands for binary digit. So
Okay.
you take the B from binary, mean two, and then digit for the it. So you get a bit.
Right.
So you have these two different states. There's 0 and 1, and that's it. So if you want to visualize it, you can imagine you have a sphere like the Earth, and say 0 is at the North Pole,
Hmm.
and 1 is at the South Pole. And with a classical bit, that's all you have: the North Pole 0 and the South Pole 1. With a quantum bit, it actually exists in what we call a superposition of 0 and 1. So what that means geometrically, I think might be the best way to explain it, is instead of the a quantum bit being restricted to the North Pole or the South Pole, it can be anywhere on the surface of this sphere.
Okay.
So, for example, if you're halfway between the North and South Poles on the equator, now you're in this combination of half 0 and half 1. Or if you're in the Northern Hemisphere, you're more 0 than you are 1. And if you're in the Southern Hemisphere, you're more 1 than you are 0. And not only does your latitude matter in terms of how far up and down you are, but your longitude around the surface of the Earth matters as well. And so, I mean, when you actually measure your qubit, then you get a classical 0 or 1. So you do only get the North or South Pole once you measure it. But while it computes, it can exist anywhere on this sphere, as opposed to only those 2 points at the North and South Poles. And so this illustrates the idea that a quantum bit is much richer than a classical bit because it can exist anywhere on the surface of the sphere instead at the poles. And from that, and it's not going to be clear why, you can actually do computation faster, along with all several other properties of quantum mechanics. But this actually highlights something else, which I don't know, maybe might be one of your questions later. But this also helps to explain why quantum computers are so sensitive to noise, and why error correcting quantum computers is such a challenge. And it's because if you have a classical bit, again, that's either 0 at the North Pole or 1 at the South Pole, in order to get an error, you have to completely flip it to the opposite pole. Whereas with a quantum bit, since it can be anywhere on the sphere, a slight bump to a different place on the sphere is now a different quantum state for that for that quantum bit or qubit. And so, these slight changes are now changing the state of your computer. Whereas, again, a classical computer, you need a complete flip in order to cause errors.
And just for a little bit of clarity as well, can you just explain a tiny bit what you exactly mean by noise?
Yeah, so essentially, you just think of noise as just any interaction with the outside world. So I mentioned that quantum bits are generally really small things. So you imagine you have a single atom. So that's you can use a part of that atom as a property of that atom as your quantum bit. And if there's any outside influence, maybe from a little like thermal noise from or some type of interaction with another atom that's nearby, that is now exerting a force or some type of interaction on your qubit, and it's changing it. But you want it to stay nice and clean and perfect.
Okay, so there's one thing that I sort of have always thought about when I've been thinking about quantum computing, and I'm actually not sure whether this is going to be a question that's far too deep. I'm not sure if it's going to be a ridiculously stupid question, or I'm not sure if it's going to be a question that won't even make sense, but I'll throw it out there anyway.
That's fine. Yeah, go ahead. Please do.
So, as you're mentioning, a normal binary system is either 0 or 1, it's off or on, right?
Right.
Now, we have so much more depth with quantum. However, the quantum world works as a function of probability.
That's right.
So, how do we rein in this function of probability? Zeros and ones are easy. We can just choose one or the other. How do we rein in this function of probability to actually do, it sounds silly, but do our bidding, do what we want them to do?
Yeah, that's good. So there's a couple things I could talk about with that. So first thing is back to this sphere analogy with the qubit. So I mentioned if the qubit, quantum bit, is at the equator, halfway between 0 and 1, and if you measure that quantum bit, I'm telling you that you either get the North Pole or the South Pole. And you can just reason, well, if it's halfway between the North and South poles because it's at the equator, then with probability a half, you'd get the North Pole, and with probability a half, you'd get the South Pole. Or, if your cubit is somewhere in the northern hemisphere, if you were to measure it, now you're more likely to get the North Pole and you're less likely to get the South Pole. And so there are these probabilities that are built into quantum mechanics and in quantum bits where when you measure your qubit, you actually just get a 0 or a 1, but with some probability. So what makes these probabilities extra unique, extra quantum, is that the states are actually described using complex numbers.
Okay.
And so it's going to be some complex number or some coefficient times 0 plus some complex number or coefficient times 1. And in order to get the probability, you have to take the norm square, or just take the like length of that complex number. And that gives you your probability. Okay, so the reason why that's different is with the probability, you can only have numbers between 0 and 1. You can't have a negative probability. I can't ask you, like, flip a coin, what's the probability of getting heads? And you say, like, negatives 0.3. It's like, that's just nonsense, right? Probability has to be between 0 and 1. But if your quantum probabilities, and I'm trying to avoid using technical terms. Like,
I know it's difficult.
These quantum probabilities, if you will, these are actually complex numbers, which means that they can be negative, which means you can actually add these probabilities together and they can cancel out. And you can't get that with a normal probability. And so you can think of these quantum probabilities, again, because they can add up and get bigger, or they can add up and cancel out. You can think of them like waves where there's constructive and destructive interference. So essentially, we're computing using these quantum waves. And you want to tune your algorithm so that the wrong answers end up canceling out and the right answers add up to be stronger probabilities, so that when you measure your quantum bits at the end of the computation, the result it gives you is the right answer.
So the sum of the probabilities, basically.
Basically, yeah. I mean, there's more like technicality to that, but but the general idea of that, yes, I'd say yes.
Interesting. Yeah. Okay. So now, I suppose in terms of the actual research that you do and many people around the globe do, is this, again, this is potentially a bit of a silly question, but is there a clear-cut path of what you are doing? Is there basically a line of hurdles that you need to do to get to the final or close to a final goal? Or is it more like you're at the forefront of understanding, and every new step you get, you're suddenly in the dark again and you need to find which way you're going?
I'd say it's somewhere in the middle, which is obviously a very safe answer, but let me
good choice.
Let me expand on that. There are certain hurdles that we know for sure. So in some sense, there is a roadmap. For example, I mentioned how quantum computers are very vulnerable to noise. And so we need a way to fix those errors. And so that's a very clear hurdle, where in order to get quantum computers, we need to be able to solve this noise problem. So that's a very clear hurdle. And there's other hurdles like that, where we have a very clear roadmap. What do we need to go from where we are now to a fully functioning quantum computer that's error corrected and that is programmable and everything? What approach to take in order to meet those hurdles? That's where it's less certain. So even on the hardware front, there are many different approaches to how to build these quantum computers, and there's not one approach that has clearly won. And so, like, for example, with our current computers, basically they're all made out of silicon, like all of our processors. And that's because of the advent of the transistor. Whereas with a quantum computer, there are people that are trying to build them using semiconductors, using superconductors, using trapped ions, which are charged atoms. There are other scientists who are trying to use particles of light, photons, and many other approaches. And they all have their pros and cons. And there's not one hardware approach that has clearly won yet. And it's actually quite interesting because different labs at universities and even different tech companies are exploring completely different options. And so, what is being pursued by one well-established tech company with plenty of resources and knowledge at their fingertips can be completely different from another tech company that also
Interesting.
has plenty of experts in the field. And so it's we don't yet have that quantum version of a transistor that's that
The
clear
universal,
universal way that we should build a quantum computer. Um, so in that regard, we are still searching in a way
right.
for which road is the best one to take.
And I suppose as well, with a quantum computer, I'm not dusting off my desk, putting the quantum computer on the desk next to my cup of coffee, plugging it into the outlet. I suspect the conditions in which you need to do this are a lot more different.
Yes, because again, because of how vulnerable quantum things are to noise, they generally need a lot of ways to isolate your quantum system. In many of the experiments, the quantum chips have to be cooled to very, very low temperatures. Right. And so you need a lot of hardware supporting your actual quantum bits in order to make them possible. And so it's not a small thing like that you just plug in. There's typically a lot of control
and energy as well, suspect
infrastructure and energy. Yeah.
Right. Okay.
So, which is kind of interesting. I mean, we're essentially using classical electronics, classical computers as a support network to build quantum computers.
This other thing, yeah.
Yeah. So it's like, I see this very intimate relationship between classical and quantum computing, where at least with what we currently have, it's not like once we get a quantum computer, we're going to all toss out our classical computers and just switch to quantum. Classical computers are very good at what they do.
Right.
We have decades and decades and decades of experience building and improving classical computers, and they are still valuable tools. And we're actually using them as tools to build quantum computers.
Right. Yeah, that's interesting. I think it's quite almost an interesting philosophical conclusion to make, that you need this support system to have something else that does a separate job almost. And I guess as we're getting sort of to the last 10 minutes or so, we need to have a bit of a discussion about how we're going to apply this. Now, for you, what are the specific benefits? We've talked about they do different things, they have different abilities, they fill different gaps that maybe classical computers don't fill. What specific clear benefits do you think quantum computing has?
Well, there are many. Maybe I'll focus on one that is very relevant to the world right now, which is COVID-19, and how do you research better drugs and medicines and things like that. And so really, these are all just problems of like chemistry. Like how do these molecules, because all of these drugs and pharmaceuticals are just molecules. And so it's like, how do these molecules work? How do our bodies respond to them? And, all these things. And so the reason why creating these new pharmaceuticals is very challenging is because molecules are quantum by nature, right? I mentioned quantum things are generally atoms and particles and molecules. And so they are quantum by nature. And it's oftentimes very difficult for a classical computer to simulate what is going on with a quantum object, including molecules, because they're just two different species, right? You're using a classical thing to try to describe a quantum thing, and they're just kind of like speaking different languages almost, if you want to think of it like that. But if you have a quantum computer, it can naturally simulate a molecule because it's already quantum.
Wow. Okay.
And so, if we can simulate all these different molecules that we hope to use for different treatments, for different drugs, then that will greatly speed up the process that it takes to do this research. Because current simulations can be very slow, and certainly if you want to manufacture each molecule and actually test it, that is even slower still. And so, to have a faster way to simulate and just to run through all these different iterations of types of molecules, and you can rule out all these, that are totally not going to work from your simulations, and you focus on the hopeful ones, and you do further research in that I think that will greatly increase the pace of healthcare innovation.
That's super interesting. I've never never realized that it makes total sense though, like
Yeah.
like you said, they're speaking different languages, and suddenly you have this situation in which they're understanding of each other, and I guess that's going to have ramifications in anything that is in the very small of our universe.
Exactly.
Right, it's
Yeah.
going to have ramifications in all types of medicine, probably materials science, things like that also. It's really interesting. Now,
But interesting, it's interesting with the history,
Please.
actually. Like the at least in the West, the notion of quantum computing was first proposed by Richard Feynman, who's a Nobel laureate. It was
I did not realize it was Richard Feynman.
Yeah.
Amazing.
Yeah, at least in the West. I mean, independently, there was also a Soviet scientist who had similar ideas.
Okay.
But obviously, during that era, there wasn't as much knowledge of what was going on in the two
Very
countries.
muddled up, shall we say?
Yes, exactly. But at least in the West, it was Feynman who really, brought this to the forefront, and his motivation was actually this application of simulating quantum physics. Like, our current computers seem to not be good at it. We don't have a proof of that, but just all the evidence is just indicating that it's very hard as far as we can tell. But if we can build a quantum mechanical computer that's already quantum, then it could simulate something else that's quantum much more easily. And so all the modern applications of quantum computers, these are modern applications. The original application was actually simulating quantum physics.
Interesting. Okay, it's amazing that it came out of a place of pure science as well, and not necessarily industry. That's great.
Yeah.
I want to take a moment to talk to you about the Sleep Science podcast. If you listened to the previous series I did on sleep and want to learn more, there really is no better place, as this podcast is a collection of interviews between sleep expert Penny Lewis and a series of her neuroscientific colleagues, and the episodes give the lowdown on everything from memory replay in sleep to lucid dreaming and how sleep can be engineered for cognitive benefit. So, if you are looking for more science content like The Blunt Report, go check out the first series of the Sleep Science podcast on any podcast provider. And on the flip side to that, you obviously spend a lot of time thinking and pondering and keeping up with all the latest research. On the flip side to that, do you have any specific standout concerns of what could come about from the advent of high-level quantum computers in terms of what they could develop, in terms of how the market might be with them, in terms of the way businesses might handle them? Any specific concerns?
Well, there certainly are. And in fact, there's actually a group of companies and other stakeholders that are thinking about quantum ethics. You have this new fancy quantum computer that can solve certain things faster. Like, are there any ethical things that we need to keep in mind? And so this is actually something that people are talking about. I mean, so there are certain specifics. I mean, one very common example, which also illustrates something that quantum computers are better than classical computers is factoring large numbers. So if I give you a giant number and I want you to actually maybe I'll take a step back with simpler example. Factoring is just to break up a number into so for example, if I give you a number 15, ask you to factor it, you factor it into 3 times 5.
Right.
So if I give you another number 21, factor this, so it's just 3 times 7, right? So
how you can multiply it and make that
exactly
number. Yes.
So it turns out that this is actually a very hard problem if you have a really big number,
because there's so many
ways.
So
if you have a really big number, that's a product of 2 prime numbers, then there's basically only one way to factor it, and it's to find those 2 primes. So it turns out that this is really hard as far as we know for our current classical computers, and this is actually underpins how we encode information and secure it to send it over the internet. So anytime you buy something online or do a bank transaction through like an ATM, our computers are using the difficulty of factoring in order to securely send your bank information across the internet. And the idea being that in order for a hacker to decode your sensitive information, they'd have to be able to factor.
Right, which is a hard problem anyway.
Right. And so the idea is that by the time classical computers are powerful enough to do that, it might be 30 years down the line, and those old bank transactions aren't valuable anymore. There's nothing that a hacker could use, And so it turns out that quantum computers actually would be fast at factoring. which means that if you suddenly had a quantum computer right now, you could actually decode all this information that people are sending over the internet, and that would have
Be very
huge,
powerful,
yeah,
shall we
it'd be
say.
very powerful, obviously.
Right.
And so one of the things that people have been working on, and actually the governments are working on new standards for how to encrypt our information that we send. And so we're basically, so within the next year or two, the world is going to switch crypto standards where we're not going to use this factoring problem anymore. We're going to use other problems that we think quantum computers also cannot break.
Okay.
And so this is a very clear example of something that we need to think about now, and make these changes now. That way, when quantum computers are available 30 years from now, or however long it takes, the current information we're sending will not be relevant anymore. Like if you wait till you have a quantum computer to switch your crypto system, then your information from the past 30 years is going to be vulnerable because it still might be important. So you need to switch now. That way, when quantum computers are available, then all the information we send from now till then will still be safe.
So that's a very specific and important and quite large issue, right?
It is.
And I guess it makes it more shaky in terms of the fact that there's no definitive timelines on when, you mentioned before when we're talking about breakthroughs versus a slower sort of product. There is some breakthroughs that might be made, and the timeline could be shifted shorter or shifted longer, and it makes it more difficult in the fact we don't know, right?
That's true, but thankfully, I don't know if you consider thankfully, it depends on if you want quantum computers to innovate more quickly or if you want to keep information safe.
Right.
Fortunately for keeping information safe, the type of quantum computer you would need in order to factor efficiently would be the fully put together error corrected quantum computer. And all the quantum processors we currently have and will probably have in the near future are all too noisy where they wouldn't be able to solve these factoring problems quickly. So thankfully in the near term, our information is safe. And so, but it's true that we don't know when that final transition will happen. And so that's why I mentioned already, like people working on the new standard for what the crypto system should be.
Okay, Tom, we're getting sort of to the end of the podcast now. Now, at the end, I always sort of like to ask, I guess, a bit of a premonition question, a crystal ball sort of question. Yeah. So for you, if you were to look into this crystal ball, this perfect quantum computing crystal ball, what do you expect to see occur? Choose whatever timeline you want. What do you think is going to the situation with quantum computing is going to look like in the future? Is it going to be something like, should we say, nuclear fusion that's always been 30 years away? Is it going to be something that's going to occur and then things are really going to be different, or is it going to be more subtle? What do you think?
I think that it's thankfully not going to be like fusion, where it's always 20 years away. Right. And I think a big reason for that is because the pace of innovation has sped up a lot with the introduction of industry players and with coordinated efforts by various governments. And so, like even in the U.S. in 2018, the Congress passed the National Quantum Initiative Act, and this was one of the few bipartisan things that Congress has done. It's passed very easily, and President Trump signed it into law. It was basically establishes a national funding and a national strategy for how to advance quantum computing in the U.S. and other governments have done this as well. So even in Europe, there's a big EU similar thing that was passed even earlier than the one in the U.S. Basically, we're seeing these coordinated strategies by governments to get industry and business and national labs all involved and working together in order to advance quantum computing. So we've seen things grow very rapidly, and we do have rudimentary quantum processors that are available now. So many of them you can access online on the cloud. Some of them are publicly available. So IBM was the first to put theirs publicly available on the cloud. So anyone can sign on, and you can actually run little programs on the real quantum processors.
Wow.
And so, these aren't big enough yet to do anything useful, but I think actually in the near term, maybe within the next 5 years, we'll find some useful uses for these noisy quantum processors. So even though we won't have a full-fledged quantum computer by then, we'll have some things that I think we'll be able to find some interesting applications for. In terms of having a full-fledged quantum computer, I think that would be more in the order of maybe like 20 years. I'm just throwing out numbers. No one really knows.
Of course. We won't hold you to it.
Yeah, thank you.
I won't call you in 20 years.
Yeah, but for that, it's a longer timeline, but it's not like 100 years. I think we'll see these quantum computers within our lifetimes.
Okay, amazing. Again, thank you so much for sort of spending the time and explaining a few things and answering some of the potentially dumb or potentially deep questions.
No, they're great.
Thank you. And if anyone is interested in what we've talked about and sort of wants to learn a little bit more, do you have any recommendations of what they can look up, what they can read?
I would just search on YouTube. If you look at quantum computing is established now, thankfully, with all the media attention, that there are plenty of resources and talks online where you can learn about quantum computing. A lot of companies have a lot of free resources to learn about quantum computing. So IBM has a free textbook online.
Wow.
And a whole summer school where they uploaded YouTube videos. Plenty of universities have uploaded similar educational materials, various things like that. And so, there are standard textbooks, but we're living in a very interesting era where you actually don't even, in some sense, need to look at these traditional means of learning where things are so available online. So I would just look online.
Perfect, Tom. Well, again, thank you so much for your time.
You're very welcome.
If you enjoyed what you listened to or have any feedback, or if you just want to say hello, please help out by visiting The Blunt Report on social media, giving a rating, or even telling a friend about what you listened to. The podcast is available on all platforms, including video podcasts on YouTube, or can be found at thebluntReport.com.